Okay, so today, what we're going to do today, Professor, I don't know if you want to say something before we get started regarding deep learning and introduction to deep learning and how this is used to, it's actually graph machine learning or deep learning, in fact. Professor, do you want to say anything?
Okay. No, okay. Yes. Okay. Deep learning is a very important topic now. Nearly all intelligent gadgets and all this fuss about artificial intelligence, it's have to do with deep learning. Uh, in this course, we are going to take a view of machine learning and deep learning regarding networks and graphs. This is a new area of machine and deep learning called graph machine learning. This is a very hot topic now. It's very used today. So these sessions have to do with this new topic. So until now, it's classic network science, and in these sessions we are going to see how could we use machine learning for how to use graph for machine learning. I this I guess this is what I have to say.
Okay, thank you, Professor. Okay, yes. Yeah, this is, as the professor was saying, a very hot topic. And so this is just going to be a crash course, a quick overview on what this graph deep learning is about. Professor Fabio Gonzalez is the one who is in charge of this. Unfortunately, he cannot be with us today, but no worries. So we have this video, and what I'm going to do is I'm going to play it, and if you have any doubts, any questions, I'll be there to answer any questions regarding this. Or to, if I consider it convenient, I could add something about it. Okay, so let me just, oh, I think I can remove the captions. Let me just, yeah.
Okay, excellent. So
Okay, so we'll get started then. So, oh, by the way, this is a last term's talk by Professor Gonzalez. So we're going to follow the video, and then in the middle of the session, we are going to go over some collab there, some notebook, Python notebook. Let me just wait while it buffers, and then I guess I can do it while the video buffers. So it's loading. Just 1 second. I was actually watching it, but then what happened was I rebooted my computer, so that's why I has to load it again. This is 2 seconds.
perfect. Okay, excellent. So you should, yeah, my screen is there. So yeah, today's session, we will have like 3 parts. One part we are going to make a quick discussion about deep learning, just to I know that most of you are already familiar with some of the concepts. Probably some of you are also familiar with the details.
Hang on, before we continue, I would like to who of you are not familiar with the basics of deep learning or machine learning in general? Just raise your hand or thumbs up rather. Okay, so who was this? Let me see. So we have one person, but he's gonna give still an overview. But if you have any questions, please don't hesitate to ask. Okay, who has not implemented any let's say neural network using like Python or Google Colab, Keras or TensorFlow? Who hasn't? who has not implemented a neural network. Okay, just so you might be familiar with it. Let me see. Oh, let me see. I'm not so sure. Would be. I just hear some beeps, but I didn't know who actually did it. But I guess we have a couple. But anyways, no worries. No worries. So let me just play this, and then if you have any questions, please feel free to ask.
And probably some of you are already experts. Okay, so but the focus today is really to how to apply deep learning to network science, and in particular, we are going to talk about graph neural networks. But I think it's good idea to start talking a little bit about the generalities of this topic, and how a graph neural networks are like a part of all these body of knowledge that is and we which is also growing very fast, which is now deep learning. Okay, okay, so I will start. Also, you were supposed to review some of the material, because the last.
Okay, disclaimer. So we didn't post you the material, but no worries. I'm gonna share the collab afterwards. Okay, so no worries.
Okay, the first part is this discussion about general about deep learning. And then we are going also to discuss a little bit about the material that you have to review. And the second part, we are going to talk about how to deal with graph data using neural networks, and in particular, deep neural networks. And the last part is going to be a hands-on, a kind of a workshop. So the idea is that we will work together to build a model, or actually a couple of models. So that part is going to be more interactive, and that's why I asked you to get familiar with TensorFlow, the and Keras. I know that it's a short time, but at least to get a general idea of how to use these tools. Okay, so deep learning. So the first thing about deep learning that okay, I will skip this. That I want to highlight is that despite the fact that this is like a hot topic nowadays, and everybody's talking about this is not actually a new idea. Actually, it's an old idea. And both machine learning and neural networks are probably as old as, in general, digital computing. So this is a timeline of neural networks, and you see that it starts in 1943, 80 years ago. Okay, so the first ideas of neural networks started at that time. And you see that yellow curve there that looks like kind of wave, and is to illustrate the fact that actually neural networks are had been like through different stages, where at some time they were like at the top, they were very popular. At other times they were like out of fashion. So this is interesting also to know that we have like a peak of neural networks during the 50s, then again during the 80s and 90s, and now again like 10 years ago, this wave of deep learning and all that is like the third peak of neural networks. So this, I think this is interesting to have this in context. So the idea of neural networks really starts.
Sorry, I wanna just maybe make some comment regarding this, just to you you have a general overview about what are. Okay, so artificial neural networks are part of artificial intelligence. But maybe you guys, younger people, you just think that artificial intelligence is just about deep learning. But I found this chart, which I liked it very much. So artificial intelligence has a lot of concepts and methods, and it's been around since the 50s last century. But here there are some big branches, like here we have fuzzy logic. So there are several methods there based on fuzzy logic. We have also some other systems based on logic, rule-based systems, but these are different types of logic. And then we have here what they call expert systems, which was very popular until the 80s, right? Expert systems. So this whole branch, fuzzy logic, expert systems, and there are a bunch of methods that are AI-based meta heuristics. And you have evolutionary algorithms. There are many families of evolutionary algorithms. They were very popular in the 90s, and now they're still very, like consolidated and broadly used. Physics-based algorithms, in which one of the most popular algorithms is a simulated annealing, and there are so many others that are based on physics. And now there are some on deep learning that are based on physics. Bio-inspired algorithms such as artificial immune systems, clonal selection algorithms, dendritic cell algorithms, bacterial foraging optimization. There is also swarm optimization and colony optimization, big colony optimization, particle swarm optimization, and so on. Okay? So all of this is what artificial intelligence is about. And here we have, in this pinky branch, we have artificial neural networks. And also, as Professor Fabio was saying, they come back to from the 40s, actually, last century. They were like proposed. Though the seminal studies, the original studies actually come from the end of the 19th century. So from neurosciences. So that they gave like the basics from biological experimentation, and then in the 40s is when you get the actual model that he's going to explain afterwards. And we have two types of neural networks. So were very popular, and the general theory is actually there since the 80s. And these are what we call now shallow learning techniques. And the most recent ones, like maybe less than actually 20 years back, is what we call deep learning techniques, or deep learning deep neural networks. And we have here some of this branch. Some of them are actually based on the original ones that were shallow neural networks. Okay, so this is very important because people think that this is artificial intelligence is just this branch, what is popular today, but there is artificial intelligence is all this. So I think this is important that you have that in mind. And also that artificial intelligence has a lot of methods, and a branch or a part of artificial intelligence is what we call machine learning, and deep learning is just a part of machine learning. So these are like the most recent developments on neural networks. So these are neural networks, and machine learning, you have neural networks and many other techniques. And now I'll continue with Professor Fabio's video. And he's going to explain what the basics of neural networks. Very, very quickly, though. Is it? No, this isn't it. This is it. This. Okay, so I'll allow Professor video to go on.
Starts with this paper. It's a paper from a mathematician and a neurophysiologist, Matt Collett and Pitts, and basically they propose the idea of what artificial neuron is. Okay, this is a very interesting word, because actually at that time, in that paper they show that neural network, which is a system made of those artificial neurons, was able to have was as powerful as any other computing device. So actually, it was equivalent to a Turing machine, which is our model of computation. We say that something which is equivalent to a Turing machine is something that has universal computation ability, and they showed that at that time. So it's very powerful. Actually, these days, everybody is talking about artificial intelligence. Probably you have heard about Wolfram, is a mathematician, the designer of Mathematica. And there is a website, Wolfram Alpha, where you can use Mathematica through the web, and he was talking about all these things that are happening with ChatGPT and all that. He was talking about this, and he was saying, see, basically the concepts that we are applying right now are pretty much what these couple of guys invented 80 years ago. There are some new things, but pretty much is basically those ideas, which I found very interesting. So there were some early works of in 1957 is the work of Rosenblatt that invented the perceptron, that was like a hardware implementation of neural networks. And then during at the end, or during the 60s, this book was very, very influential. It was a very critical book of neural networks. Basically, one of the fathers, Marvin Minsky, and two of the fathers of artificial intelligence, was saying, see, the neural networks are not a way to build artificial intelligence systems. We are not going to get far trying to simulate the brain. We have to do another approach. And basically, they at that time they almost buried neural networks. So people moved from neural networks to work to other things, and this wave is what I was telling you. So something was very important during the 80s was the invention of backpropagation, which is actually the discovery, because backpropagation was invented in some other context. But actually, what happens was that this guy Hinton discovered backpropagation or proposed backpropagation as a mechanism to train neural networks. So this basically gave us the possibility of training more complex neural networks, more complex than the perceptron. So it was very important. And then there was like during the end of the 80s and during the 90s, really a lot of interest on neural networks. And actually, Professor Luis Fernando and myself have the opportunity to live through that interesting time of this second wave of popularity of neural networks. So actually, Professor Luis Fernando is one of the pioneers of the work on neural networks in our country. At that time, I was finishing my bachelor, and Professor Luis Fernando, who started very, very young. I mean, we are almost the same age. He was already a professor, and he organized the first Congress on neural networks in our country with Professor Germán Hernández and Professor Luz Gloria Torres. So that was also an interesting stage. However, during that time, really this was still very academic. Some applications, some real practical application, but they were really very few. And it was more a topic like of interest in academy and research. Okay, and again came other methods. For instance, that book is a book from Vladimir Babnik that proposed the support vector machines, and so methods with more mathematics and all that. Uh, Again, neural networks went out of fashion, and okay, I will move on, and then we are living through the third wave of popularity of neural networks. So these are some news from uh, about and nowadays there are many more news and many new things and applications of neural networks. And actually, everybody is using permanently neural networks in our cell phones, when we use our computer, when we use a search engine, when we use different services. Neural networks are everywhere nowadays. Okay, and all this is because of this deep learning boom. Okay, so okay, I will move here. And yeah, also the idea of having a large neural network, which is basically deep learning. So deep really refers to the fact that I can have a neural network that has several layers. Okay, so the depth here refers to that, to the number of layers that a neural network may have. That's an old idea. What happens is that we didn't have the algorithms and computers powerful enough to train those large neural networks. So actually, those ideas or those algorithms that start to be successful started at the like 15 years ago. Probably this is one of the okay. This is one of the old models which were we can consider like deep learning, but this is one of the first papers that use the word deep, okay, when referring to a neural network. That's from 2007, 2006, actually, also from Hinton, okay. And this started like actually the people that was working during the 80s and 90s in neural networks, some of them continue to work on that, despite the fact that many of the people working on machine learning moved to other kind of methods and algorithms. However, they just continues to work, and finally they made it work, and they were able to train large model. But the presentation in society of neural networks was really this. This event was very important. It was a challenge for recognizing objects uh, uh, in images. It is called the ImageNet Challenge, and at that time, we are talking about 10 years ago. This was a very complex task because of the number of images that you have to use to train your model. It was 1 million. And then the number of concepts or different objects that you have to identify, those were 1,000 concepts. So the best models before deep learning have performances around 30% of error, okay, on this task. And in 2012, there was a new team that basically cut the error on half. So they got a performance around 15%, which is very, very unusual in these kind of challenges that are very popular in machine learning. Typically, the improvement from year to year is 1-2%, but these guys cut the error to half. So everybody was looking. So what was these people doing? And actually, what they were doing was doing deep learning. This is the model that's called AlexNet. It's a neural network with 8 layers and with around 60 million parameters, which was huge for that time. So that was like the presentation in society of neural networks. Okay, so was no neural network but deep learning. So what was deep learning? So I like to call it like a kind of recipe. Okay, because there are several elements. See that one element which is very important for this recipe, which is the idea of neural network. We know that from 80 years ago. So that was not enough to have the idea of artificial neuron or are combining neurons and things like that. So that was not enough. Really, deep learning is like a confluence of different factors that made it possible. Okay, so that's what I call the recipe, the deep learning recipe. Okay, so these are the elements of the recipe. So one element is the approach, to do machine learning change. Typically and previously, before deep learning, this is what you see there is like the typical workflow in machine learning. You have your data, images, tests, etc. Then you have a process and actually a stage where you pre-process your data and then you extract features. It was very specialized because the kind of features that you extract for tests are different to the kind of features that you may extract from images or from graphs. So actually people was doing machine learning on graphs long ago, probably from the 80s, 90s, probably the people were already doing in different kind of data. However, you have to do this by hand, manually, okay? Because typically a machine learning model works with vectors, with numerical data. Most of the algorithms work with numerical data. So this feature extraction was very important, okay? For instance, if we are dealing with graphs, which is the topic of this course, we have to think how to extract those numbers from graphs. But you already know that there are different quantities that you can't calculate from a graph. So the average degree, the centrality, right? The clustering coefficient, etc., etc. So different quantities that you can extract for instance, from graphs. Same thing from images, same things for tests, etc. Okay, and then you do model learning. You apply your machine learning algorithm. Then you get a model, and then typically you iterate this. You evaluate, then you improve. You evaluate, you improve. You evaluate, you improve. And when you are happy with the performance of your model, you can use it to predict over new data, okay? So that was pre-deep learning. What happened with deep learning? This change. Basically, the one of the elements, important elements of deep learning is the realization that you can also learn the features from your data.
Okay, let me just stop here for a bit. And I maybe would like to reinforce, or probably because I think he went a little bit too fast, Professor Fabio, on the introduction to, and I'm gonna do it quickly as well, but just to highlight a couple of concepts that are very important. So what happened was, so as I was mentioning, actually, at the end of the 19th century, actually, one of the scientists who actually was awarded the Nobel Prize in medicine, what we call it, that is called physiology, Ramon y Cajal, actually Spanish guy. They were performing some studies, on how the neurons worked, in the lab. So the general idea is that, a neuron, individual neuron, just gets a stimulus from the outside, and then, or from other neurons, they get some signals from, just now think about that they come from other neurons. They perform, this is a cell actually, a neuron is just one type of cell. It has a nucleus here, and here it performs some process there, and then depending on the stimulus that it receives from the other neurons, then it produces or generates a signal here that is sent to the other neurons that it is connected with. Okay, so receive some inputs from other neurons from the outside, perform some processing here, and then produces an output signal. that is sent out to the other neurons in general. Just think about input from some neurons, process them, the signals, and produces some signal. One particular signal is sent to other neurons that it is connected with. And then what Professor was saying is that they actually propose a very nice and very simple model in which they actually have they represent here, and is the basic, is the actual model that is being used currently today. Is the same model that they introduced in the 1943. So here you have like the representation of each one of the signals that come from the outside. Okay, come from the outside. Here there are two processes. It's just a sum. Here is a weighted sum. The process is actually very simple. It's just pure arithmetic. It's this number multiplied by this, what is called the synaptic weight. I'm going to go a little bit fast on this. And they just, it's a product. This times this, plus this time this number times this, and so on. And then at the end, you get the actual stimulus or a measure of how the neuron is being stimulated. And then this gives you a number, just a real number. And then you compute here a function, the nonlinear function, what is called the activation function. And then the output of the neuron is being produced, the state of the neuron, we call it. Okay, and so what has changed since then is that maybe you play, especially with this function, you change. There are different types of functions here, activation functions. Some of them are, this was the original one by Maculo Campitz, but then you have the sigmoid, which was very popular in the 90s. Now we have, you have this ramp, you have sines, you have Gaussian, you have ReLU. Here we don't have it. Just a linear. This is a ReLU actually, truncated. It's not the general linear function, but rather before a certain number is 0, and then after a certain number is 1, and it's truncated somehow, cropped the function. So that's what changes from one. So that's but the general model, the original model is still the same, and that's what Professor was saying. And then what you do, this is just a single neuron. And when you connect them, you have a neural network. And to connect them, you have what we have here. We have been studying this class. So you can connect the neurons the way you want. So we have here several graphs that represent different types of neural network. This is the most popular type of connective of graphs, which in somehow represents the way that the nervous system works. So you have some specialized input neurons, then you have the processing layers. This is organizing layers. And then at the end, you produce an output. And the signals just flow in one single direction. So this is a directed graph. So in general, these are all directed graphs. Here, we have a Hopfield network. So this is, how do we call this graph, by the way? What type of graph is this? You know it already, right?
Complete.
Exactly, right? And we have here the coherence self-organizing map or coherence neural network. We have just two layers, and the output layers of neurons are organized in an array, a grid. Especially usually it's a rectangular grid like this one. Or we have the multi-layer perception. So very important. So it's not only connecting the neurons, but you need to, by the way, here you have here in between each one of these connections, this is a label graph. You have some numbers that represent the weights of the connection, the synaptic weights. And then at the end, what you need to find, so this, to make some use of the neural networks is you need to produce a good combination of all these numbers that at the end, when you give an input, it produces the expected output. So the main problem here is what is the right combination of numbers here between all these neurons, all these synaptic weights that at the end have the neural network do what I want it to do. Okay, so you can connect them, but you need to provide a way to find these weights, and that's what we call a learning algorithm. Okay, and that's why the one that Professor was mentioning, the backpropagation algorithm, was very important in the United States because it provided a general way to find those numbers in a computational manner, and it's very supporting in some theorems from I don't know, Paula is here. It may be, I think, maybe a real analysis or something, analysis, a functional analysis, and it's actually from the beginning of the 19th century. So, sorry, the 20th century, sorry, the 20th century. Okay, so it's like more than 100 years back, the basics, the foundations of this algorithm. And what Geoffrey Hinton did was to adapt it to be implemented in neural networks. Okay, so in the end, you have single neurons. Okay, you have single neurons that are inspired by these biological neural networks. You have the model of the neuron, which is very simple, indeed, very easy to compute, and you can connect them all these neurons, and you form a graph, and then you have a neural network. So this is a way to do it. This is another way. These are just a few examples. You have also these recurrent neural networks. You know, as opposed to this one, which when the connections are going on one single direction, in these other type of neural networks, some connections go back to the previous neuron. Like in this case, you have one connection going forward, and then you have another connection going backward. And you also have this other type of neural networks, like convolutional neural networks that he's going to mention later, and then I think I can stop there. You have combination. I can stop here, and then we can go back. This is by the way some application of coupled neural networks. But maybe I would like to just highlight this in what is shown in this slide. You know. So, for example, if what you get, if what the neural network gets as input is an image, then what you do is you put in one row next to the other, and then what you get is the matrix becomes a vector, and that's what's going to be the input to the neural network, for example, and then all the processing occurs there in the intermediate layers or hidden layers of the neural network. At the end, you get the output. That's one way to use it. Or like in this example, you get an image, for example, at the end. So what you get here is a vector that represents an image. In this case, it's a face, a particular face. And at the end, it can tell you whether it's one person or something like that. Or you know, the hello world of the deep learning is cats and dogs. So here we have images of cats and dogs. So at in the output, what you get is whether the image corresponds to a dog or to a cat, for example. Okay, so I guess I'll go back to Professor Fabio's video. Thank you. Okay. I have to share now. This. Okay, let me see. There is a question. Ivan says, does a neural network allow for the constitution? Can you develop? What do you mean constitution of a neural network or to a machine?
Yeah, good evening. So it's actually, I mean, perhaps constitutions too much construction as well. I mean, can you possibly like understand a neural network as a Turing machine? That is the question. So
actually, the relation between or maybe a comparison is what maybe Professor was saying. You know, like what was demonstrating, and mathematically, I know you like math and you study math, aren't you? Is that, you know, whatever you can do on Turing machine, you can do it on a neural network. You know, so they are equally powerful. You know, that's what is being tested there. But the way that they process the information is different. You know, and maybe a general idea, just so you maybe go, maybe you have studied it already, but it's like digital computers today, you know, like they are based on these digital gates, you know, like AND, OR, XOR, and that. So one way to understand it intuitively is that you can implement all those digital gates, you know, or logic binary gates like are and not, or you can implement them with just single perceptors, for example. And then just by combining them, you can build a neural network that can just do whatever a digital computer can do, just by implementing these electronical actually gates, electronic gates. Okay, okay. Let me just. That's an intuition. Okay, and it's maybe not too hard to show it. But the demonstration, right, Paula, is just based on logic, on propositional logic. Okay, or Boolean algebra. Okay, and it's easy to understand. Okay, let me just move on.
Okay, that you can in principle give the raw data to your model and let your model learn to extract features. For instance, in the case of images, the input is an image, which is basically a set of pixels, right? So basically what a neural network for image analysis, for image classification, and any other kind of tasks on images, typically convolutional neural network, basically what they do is this. They learn hierarchically different features that characterize the content of the images. So at the base, they, for instance, learn features such as edges. And then in the next layers, those edges are combined to learn or to represent object parts. And then in the superior layers, you may have concepts that are like models of whole objects and things like that. Okay, so that was a change on the perspective. Okay, these are the ideas were not new. The thing is that, as we will see, at that time we have the computational power, we have the data that made this possible. Okay, okay. So the second component, which is very important for deep learning, is the size. Okay, so deep means bigger models. Okay, this graph here is is showing us the evolution through the years of the models that won the competition, that competition of object classification, the ImageNet competition that we were talking about. So this here, the time years go backwards. So this is 2010, 2011, etc. This is 2015. Okay, and these are models which are predictive learning. That's the way that they call shallow models. Okay, so you see that the error was around 25, 28, and then 2012 is when AlexNet came, and the error was reduced to 16, and then and so on. You see that year after year the error was going down. So this is from the group of Alex Krichevsky and Hinton. Alex Krichevsky was the student of Hinton in the University of Toronto. This is from a university in Oxford, BGG, some model that is still used. This was Google Net from Google in 2014, and ResNet, which is still used, which is a model from Microsoft. But in addition to reduce the error, see that the error, and nowadays is even below this very small error. Here you see the increase on the size of the neural networks. Okay, so the first deep neural network were only 8 layers. The size was 8 layers, then 19 layers, then 22 layers, and in 2015, 152 layers. And this hasn't stopped. Nowadays, you maybe had been seeing the news and reading the news, listening to different all the different things that are happening with ChatGPT. And in the case of here, we are talking about with models with tens of millions of parameters. with large language models, we are talking about thousands on millions of parameters, billions, and almost probably the models are coming will be probably in the order of trillions. Trillions, okay, no our trillions, but the English trillions, okay, which are millions of parameters. So these are huge models, okay. Okay, so that's the other element. Uh, to train this large model, you need a lot of data. So that's the other element, that data became more and more available because of mainly, yeah, in part because of information systems, but really the main reason for having all this amount of data is internet, okay? But data alone was not enough. Okay, so something very important is the early stages of deep learning were mainly devoted to supervised learning. So you need data which is annotated. Okay, so this was also very important. The fact that there were efforts, for instance, ImageNet is an effort from a professor at that time in the Stanford University, Li Feifei, that collected a large amount of images. This was like the numbers from 5 years ago. Probably today they have much more than that. At that time, they have like almost 15 million images annotated with 20,000 concepts with bounding boxes in some cases around the objects. And all that was possible because people, real people, humans, annotated manually those images. They use crowdsourcing to do that. And nowadays that continues to be very important, that you have people, humans annotating data. So that's is not um, uh, enough to have just data. You need also to annotate data. Many of the models of these days are models that use strategies like self-supervised learning. Okay, for instance, GPT is a self-supervised model that didn't need annotation in the test. However, taking GPT, which is a language model, and make ChatGPT needed annotated data. They use people from, actually, there was some criticism because they use people from Kenya. They pay like $2 per hour to the annotation. So they were saying that they were exploiting that people and on that. But if they pay $2 in Kenya or here, actually that's not bad. Okay. But what I want to emphasize is that having people annotating data is very important, and that's something that also enable the deep learning. So having large models and large amounts of data, you really need computational power. Okay, very important to have computational power, and that was possible because of the GPUs, graphical processing units. Okay, so the graphical processing units are specialized hardware that initially was intended for making graphics faster in computers. Okay, however, uh, scientists realize that you can use that for doing scientific computing, to do calculus which are expensive. In particular, because doing graphics, like doing rendering, the rendering for doing like movies or for doing video games, requires basically linear algebra, to do linear algebra in a very fast way. So that's exactly what you need for many applications in the scientific computing, for simulation, physical simulation, and in particular for machine learning. What you need for doing machine learning is fast linear algebra. And GPUs are really good at that. Okay. So thanks to the demand basically from gamers, there was like an scale economy that allowed those that hardware to be very cheap. Very cheap. I mean that nowadays you can buy with by 1 million, 1.5 million, a good graphic card that you can put in your computer, right? So that made like a democratization of high performance computing, because actually having this kind of performance in terms of this is measured in terms of flops, teraflops. Uh, 10 or 15 years ago, it was required to have basically a supercomputer. Yes, Professor Alfonso, please go ahead.
Yes, Dr. Fabio, I have a small question. Do you hear me?
Yes, I hear you.
Okay, it's a very small question. Quantum computing has a space here. Is research in quantum computing pointing to deep learning?
Actually, that could be the next step. If we someday can have a practical quantum computers, because that will really accelerate not only machine learning, but many other kind of applications. But in particular, machine learning, definitely, we have a quantum computer. The problem is that we don't have a practical quantum computer yet. We have quantum computers and we can already use quantum computers. But the problem with those quantum computers is that one thing is that the size is not very large. They have like in the order of 100 of qubits, the last ones. And but the main problem is the noise of those computers. So there are still challenges. But if actually, I would be no surprise really if that happens soon. I'm really surprised with what is happening with artificial intelligence nowadays. So if that happens next year, I will not be surprised. But really, it's difficult to predict when we are going to have quantum computers. But that will be definitely the next stage. Lina Maria.
Yes, teacher. I have a question because we are talking about the network science, machine learning, deep
Right.
learning, and I want to know what is the difference or what is the branch in these topics, because you in this moment you are talking about the hardware, but in the content I see that we talk about the models or the algorithms or the APIs that we use are the tools, and I feel that the goal is the same now from the data. This discover
That's
knowledge
right.
from the data, but when you say or you talk about machine learning, deep learning, I feel a little confused with the terms because
That's right. That's right. That's right. Yeah.
but
Very.
depends of the models or the architecture
No,
or the hardware.
very good question. Very good question, Lina Maria. Yes. I mean, one thing that you said, I totally agree. The goal is more or less the same, and is in general to use data and make sense of the data with different purposes. Okay. So, in the case of machine learning was the first motivation for machine learning was really as a tool to do much artificial intelligence, and that means to build systems with the ability to address complex tasks, such as
Campeón,
being
José,
able to do pattern
José,
recognition, like
José Miguel,
doing vision,
¿ya
to
hiciste tus
understand
responsabilidades?
language, to do planning. So the main focus of
No,
machine
señor,
learning
me
has been
refiero es
that.
a que si ya
However,
organizaste tu cuarto, ya lavaste la loza,
machine learning, many of the
¿seguro?
algorithms and the
Well,
approach that the
Sí, no te
machine
voy a
learning
dejar con la
use
basura.
start to find use on other applications like data.
Excuse me. The microphone is it's open. Something is happening with Miguel or whatever. I don't know. Okay. Let me just please keep your mics off as we play the video.
Analytics. So during the 80s, during the 90s, people start to talk about something which nowadays that term is not used, which is data mining, minería de datos, Okay, and the purpose of data mining was basically it's basically what we call nowadays data science, to analyze and to get information and knowledge from data. And people realize that many of the algorithms that were used and developed for doing machine learning can be used to do data analytics and doing data mining at that time. So there is like a confluence of statistics and machine learning in the context of data analytics, and then the confluence of other areas. For instance, when Professor Alfonso was talking about the roots of network science, also comes from other areas of mathematics, for instance. Okay, so really, what happens is that it's a confluence of different areas around of common problems. Okay, uh, I know it's difficult to navigate all this, but if I try to nowadays, what was the situation? What I will say is this: uh, machine learning is part of, definitely is part of artificial intelligence. So, okay, it continues to be part of artificial intelligence. However, one of the important applications on machine learning, okay, then you have artificial intelligence, then inside you have machine learning. Inside machine learning, you have neural networks, and inside neural networks, you have deep learning. Okay, because there are other models for machine learning which are different to neural networks. Okay, then you have oh yeah, okay. Daniel has a question, but I will try to finish answering Lina Maria. Then you have the applications, and then there is an intersection, because you have all this area that nowadays is called data science, and then in data science you have different problems of analytics that you can address with machine learning, but not only with machine learning, but also with the statistics. And then you have network science that is also like an intersection with data analytics, data science, but also have other problems that are not necessarily inside that part. Okay, so basically what we have is like different areas of knowledge that address some similar problems in those cases, or other problems which are not necessarily the same. Okay, I don't know if that made like the perspective more clear or clearer. Sorry, Lina Maria.
Yes, teacher. Yes, thanks for
Okay.
your answer.
Yeah, so and here I'm trying to tell you this story why we are nowadays experimenting what is happening with deep learning. Why deep learning has and deep learning in some way kind of how do you say, eclipse the other areas, because deep learning has like an application in not only in analytics but in things like autonomous vehicles, and then in the language, and in other kind of areas. And but really those are several fields of knowledge that contribute to the same kind of problems. Okay. Okay, yeah, Daniel is asking about FGPAs, yeah, FPGAs, yeah. Those are field programmable gated arrays, which are some kind of specialized circuits. Yes, there are some areas where those has been used, but what I see nowadays is that basically what is dominating is GPUs. So some people was proposing that, but I think that's very niche. And most of the work nowadays is done is with this kind of hardware. Okay, okay, I will continue. Something very important about this that has to do with what you were studying these days, that I request you to study, is that programming this kind of hardware is difficult. Okay, so actually when they started to realize that you can use GPUs to other applications, they developed some frameworks. NVIDIA, which is the leading company on this area, they developed something which is called CUDA, but that was very difficult to program. It was C, basically C, and it was very low level. So something that was very, very important also for this sources of deep learning was the development of platforms, so and the programming libraries and programming frameworks that allow to use this kind of hardware in an easy way. I mean, without really having to understand the details of how the parallelisms work and all that. So all this abstraction that is provided by frameworks like TensorFlow and all Torch, PyTorch, etc., is very important for this popularization of deep learning. So this is also very important, and that's why using these tools nowadays and working on this is very important to know at least one of these frameworks. Okay, TensorFlow is one of the popular ones, and PyTorch is also becoming in fact, is more popular in research nowadays than TensorFlow. Okay, okay, and that's something that we are going to discuss later. Okay. Okay, these are some examples of the code using CUDA, Theano, this an old model. What these kind of frameworks do inside is basically build computational graphs and optimize those computational graphs. And those computational graphs allow to easily map to the hardware, to CPU, GPU, multiple GPUs, multiple computers. But all that really is abstracted away, and as a user, you don't have to worry about that. Okay, so this is Keras, so which is the one that you were reviewing, and it's very expressive, very easy to use. Okay, so that was another element. Other important are algorithms. So there are some classic algorithms. Most of the algorithms that are used nowadays were invented during the 80s and the 90s. There are some new algorithms, some new approaches, and many, many tricks. This is very engineering. Okay, so machine learning is like a kind of pendulum. Okay, so at some times is in an extreme where the focus is more on the theory, the math, the statistics. Okay, and at other time, like right now, the focus is in the engineering part. So doing deep learning is very engineering in the sense that is a trial and error. Actually, for instance, this book, the neural networks tricks of the trade, like the literal or the translation will be something like the los trucos del negocio. Okay, you will think that is like a any book, and actually no, it's a edited book with different chapters, and all the big names in machine learning wrote a chapter in that book. Okay, so those are like the really the serious people working on neural networks, and they wrote a book about the tricks because this is full of tricks. Okay, and what are the tricks? All these are tricks, different mechanisms, different activation functions, things that made training the neural networks easier. So nowadays, if you want to build a deep learning model, you have to be aware of those tricks and you have to know those tricks. So that's actually something that I don't like that much, but no way, you have to use that and deal with that. Okay. Okay. So yeah, several applications, etc., etc., etc. Okay. So something that I asked you to review was and let me here open quickly the notebook that I asked you to review. So actually, let me share with you this. Actually, I think I will do this. Right. So let me share with you this window. Yeah, this one. So I asked you to review. Wow.
Okay, let me stop here a little bit. So I just shared, and actually this is being posted there since last time we had this class. So can you please tell me, this is actually there posted on the classroom. But can you tell me if you can access this collab, this Python notebook?
Yes, we can.
Okay, yeah. But before, since we have a, so please browse it as I maybe reinforce a couple of things about what Professor was saying that I consider that are very important and that would come up later in this session. Okay, so first thing. So let me see, can you, oh, it's here already, sorry, already open here? Yes. Open. Wait, sorry. This is,
For me, it's failing in the sixth step.
what is failing?
In the sixth step, it's failing. It says LR is duplicated in Keras Optimizer. Please
Oh,
use.
maybe solder, and so we will need to be replaced for by, I don't know. Maybe you can. Okay, I see what. So we need to go to Keras and see. But I just wanted to highlight this. Which is this is what what Professor Fari was showing about a general process in machine learning. That you have the raw data, and this is actually not only in machine learning, but rather in data analytics, particularly in machine learning. So you have the raw data, and then you have to perform some processing there, such as cleansing the data, and then you just send you straight to the sorry, to the, I don't know if I can maybe, because no. I don't know if I can download it. Maybe it's gonna be easier because it just takes me straight to the yeah, to the quiz. Yeah, sorry about that. But it's too little. Okay, now it is. Okay, so you have the raw data, you perform some cleansing and then transforming the data. Then you get the features, what we call the features, which are actually the variables. In general, you can think of variables that are going to be fed to the model to perform the modeling process, and then you get the insights about whatever the problem is. So I just wanted to make sure or highlight rather something about what happens here. You can perform after you clean the data. For example, you get the features. One way to get the features would be something as simple as, if you have 10 variables, then you maybe consider that 2 of the variables are not relevant for some reason, or you perform some mathematical analysis or statistical analysis, such as, for example, if 2 variables are highly correlated, then you just discard one of the variables, and then you get just 8 variables, and those are the features that you are going to feed to the model. Or you can perform some process here, some mathematical transformations, such as a very popular one, which is principal component analysis, for example. It's a linear transformation of the original variables, and then you get these features, okay? Or you can perform a nonlinear process there, and then you get the features, and then you do the actual model. So this was in general being done, you do with in machine learning or in data analytics. But something that happened with the development of deep learning is that previous to that, you need to do this by hand or manually by performing some process here. But with deep learning, what happens is that the neural network inside the structure, the architecture of the graph performs this analysis or this transformation. Okay, so and this is very important because in general, what happens here in machine learning is you get the original variables. Just think about in general variables or the data, and then what is important here is that you perform some mathematical transformation. You get in general it's going to be a vector, and then when you have a vector in a vector space, then you perform all the math. You can use all the math, and you use linear algebra, you use calculus, you use a functional analysis. statistics, whatever, because you have this data already in a vector space, or vector space, and then you can perform whatever type of analysis. So this is very important. So what is important nowadays is just to think that you have the raw data and you perform some transformation, and then you get a vector, and then you perform the model. And this transformation is what they call now some embedding. Embedding is just performing that particular transformation. And I wanted to show what happens, for example, in the case of what is so popular today in when it comes to text processing. This is what ChatGPT does. You get and there are many other ways to do it, and not just what ChatGPT does with a transformer, but there are some other methods to perform these embeddings. So you have the text, the original text, you perform this feature extraction, feature analysis, feature engineering by just performing some transformation here, just some mathematical transformation. And this is what's called, and you perform an embedding, and then you introduce it to the model, and then you get the model, right? So the important thing is that you have the original data, you make it a vector, and then you perform the model, the modeling process rather, okay? And then I think one was the one who was talking about this. Let's see. In general, just maybe forget about the details for now, but let's just focus on the general application of. By the way, there are of the implementation of what it actually does. But maybe you are right. One was the one who talked, right? One David. Was it you?
Yeah, that's correct.
Yeah, maybe it's the some of the functions or the syntax there, or are duplicated, and then maybe it's a newer version, to do that, a more recent and updated way to do that. Let me just let it. Okay, so what we want is you guys just to look at on your own computer, look at the notebook, and follow the explanation that Professor Fabio is going to give afterwards. Oh, sorry. I need to share the screen again. Because it's a different way to share it. Okay. This is it.
Let's see. So this is our class. Okay. So I ask you to review this. Yeah. So did you have time to take a look to this, guys?
Yes.
Okay, good. So I will quickly over this and then answer some questions if you have some questions. But I will ask you to make this more interactive about some of the things that we are doing here. So anybody that want to, we will quickly over this, but I think we can make it more interesting if you help me, guys, to quickly go over this notebook. So anybody that wants to tell us what we are going to do.
Okay, so maybe we can still do this because you are familiar with this. Most of you, at least with programming Python. Then we can maybe let me just maybe let's see. I'll just open it here. So at the end, let me see what I should focus to. So, okay, maybe I'll go back to Professor's notebook, and I'd rather show it here, and you guys can help me understand it. Some of you may have seen it something similar. Of course, there are some usually when you program at the beginning, you have to set up some things there, right? One, you should know this, right? One, David, this part. You're seeing it? Are you seeing it? No, you're not.
Yeah. I'm seeing it.
This part.
That's something that's very common when we are implementing.
Excuse me?
Yeah, that's something that is very common when we are implementing the model with Keras.
So it's just saying like we're gonna use this package, right? Okay, I'm just gonna maybe these are some functions just to plot the data, right? And at the end, the result of the classification by showing the decision um, border. Okay. So I think we should start here. What is this? I guess you might have seen this function. Who can tell me what it does? Feel free to do it, please, to speak out, make moons. It's just some toy data, just to show the example, right? What is it? Who is it? This is Freddy, right? Freddy?
Yes, I think that it's a dataset, sample of data that is gathered by scikit-learn, and it's maybe about the moon of the face. I don't know, but it's a dataset that is from available from scikit-learn.
Yeah, this is a function to generate a sample, right, Freddy? And what type of and it has some parameters to tell the computer, let's say, generate 1,000 samples with this parameter. This is regarding the noise, and I don't know whatever this parameter is in this. And what you produce is this, right, Freddy? Let me just shrink a little bit.
Yes, that produce the sample of data.
And what is this? What is how do they call this data set? Are you familiar? Well, it's actually being set here, right? What they call it? Ready?
Make moons.
Yeah. So these are like two moons, right? One facing the other one, right? This is like half one moon. What do you call it, by the way? This type of it's not the full moon, but what do you call it? Like half moon or whatever, you know? How do you call it? Not the full moon, but this just is this. Sometimes you see the moon like this, right? So this is a moon and this is the other moon. Is it clear for everyone? Thank you, Freddy. Right? By the way, Freddy, since this is it's going to be a classification example, then we have, we label the data, right, Freddy, or anyone? How does it show it there, the labels?
Yeah, there should be two classes. I think that it's called class 0 and class 1.
Okay, so we labeled the data into classes. One belongs to one of the half moons and the other one to the other half moon, right? So
Right.
we have the what is this called? Purple. The purple ones belong to class 0 and the reddish one belong to class 1, right? So this is just to generate the data that we are going to classify. How will we call this, by the way? This data set? How is it called in machine learning? But by the way, what is X train and Y train? What does it mean? You can tell me. Tell us.
The X train are the values used to be trained, that are the data, and the Y train are the labels of the train dataset.
Okay, Freddy. So we can call this the input data and these are the output data, right? Freddy? The input,
Right.
the output,
Right.
right? Okay, good. Thank you, Freddy. And here, this is what Professor Fabio was saying. Who can tell us? So this is and it's very important that he highlighted this because now I mean, building the models, as long as you know the theory, is going to be not so hard, you know, and you know, to get the good result, the result that you want, you need to perform some of the tricks or apply some of the tricks rather that Professor was talking about, Professor Fabio. Okay, what is this? So this was his question, by the way. Who can tell us? Some of you guys know this.
That's the architecture of the model.
Okay, one, can you develop, please explain? I highlighted, let me just make it bigger, because I think this is the key, what? Right, one?
Yeah, that's the architecture. So first we say that this is a sequential model, and then we start adding the layers, right?
How many
So
layers?
we are
How many layers?
Uh, it seems like 2, right? And it's just defining the number of the units. I think that are the neurons. I'm not sure. And the activation, the first case is the ReLU, and the second case is the sigmoid.
So how many layers do we have in the neural network? Let me just show this. The one. Let me just show. Maybe this will help you. This will help us to understand what I'm talking about. It's gonna be like this, right? But how many layers? One.
All right, one hidden layer and just one output layer, right? The input layer and the
Does it have one hidden layer? Can anybody confirm?
no, I don't think so. I think that it's just the input layer and the output layer.
Does everybody agree with that? Freddy, what do you say, and everybody else? Do you guys agree?
Yes.
Okay.
Yes, I'm agree.
Thumbs up, please, if you agree with what one said, or thumb down if you don't. Okay. Sergio, thumb up. Sergio, agree.
I'm agree.
Do you agree?
Yes, one hidden layer and one layer of output.
So you said one hidden layer, Sergio, or no hidden layer?
Yes, one hidden layer.
You said one hidden layer. Are you sure, everybody? One hidden layer? Yes or no?
I think that it just have the input layer and the output layer.
Okay. Who agrees? Okay, we need to agree on this. Why is that? One.
Can you repeat the question? Oh yeah, here this 20. I think it's the input layer, right? Oh no, sorry. 20, 20.
Yeah, actually, here is the explanation, right? Right, Sergio? Sergio,
Yes.
can you please read this out loud?
The model is built by stacking layers. The first layer is a dense layer that receives 2 inputs and has 20 neurons with ReLU activation.
So that's gonna be the hidden layer, Sergio. I guess I have to go and draw this. Hang on, just a second. Just to make sure, and then we can move on. Where is the Jamboard? Just a second, please. I guess we can use this. So we have Sergio again. So we have 2 inputs, right? Why 2 inputs, by the way? Who can tell me why 2 inputs?
Maybe 2 characteristics or something like that.
Sergio, and why 2 in this example?
2 classes.
Really? Freddy, can you help us?
The input should be the features. Maybe in the picture we have 2 features from -1 to 1, I think so. The position x1, y.
Exactly. Each one of the examples is a point in 2 dimensions. Okay, as you mentioned, right, Freddy? The x and the y, right? So at this point, So whatever inputs goes as input to the neural network is one of these data points, okay, which has this value, x value, and this y value. So this is a couple, right? A pair, rather, a pair. This is just a pair of numbers, right? So I'm going to use the same label as you mentioned, x and y, right? And then we have the 20 units here in the middle, Sergio, right? 20 of them. And each one of these is dense. That's why it says dense, right? One. So each one of these, or the neurons here, connect to the other one. And what is the activation function here? They said one.
ReLU.
So it's right here. And by the way, this is what I was talking about. Oh, sorry, this isn't it. Sorry, it's the other one rather. Oh shoot! Hang on. So when they say ReLU, is this function? What is the ReLU function? ReLU. So is this one? This is a ReLU function, right? But it's actually I'm going to show it here rather on the Jamboard, the board. So a ReLU function is this 0 and then becomes 1 and then 0, right? Agree?
Yes.
Yes, that's the one.
That's the ReLU. ReLU of x, and this is x. And then what is the output? 1.
There is just one, sorry, just one neuron with a sigmoid, I think. Yeah.
It says, right, Sergio? It says the second and last layer, it has a neuron with sigmoid activation. Sigmoid activation, sigmoid activation. So it's going to be just one single neuron. And this is also dense, so all of these neurons are connected to it, and this has as a activation function a sigmoid, which is like this, which is actually, yeah, maybe it's going to be nicer. It's going to be actually something like this, right? Right one?
Yeah, it's the one that.
So the output is going to be a value between 0 and 1, continuous value between 0 and 1, okay? And now let's continue with so to build this neural network, this is called model. How many lines do we have there? One, 2,
5 lines of code.
I mean, this is the part where you actually build the model. I mean, not build, but rather specify what the neural network, what is the architecture or the structure of the neural network. So one layer that receives the input that has 20 units. The input dimension is 2. It has a ReLU activation function. Then we have another layer with just a single unit, and that it has a sigmoid function as an activation function. Okay? So which is shown here, right? Here is shown, and then now we have the tricky and the good part, actually, the most important part, maybe. Can anybody help me explain this?
It defines the optimizer that are going to use to reduce the losses. It are going to use a SGD. I don't remember that recall.
Which is SGD? You can Google it, but let me just maybe give an idea. So at the end, what you want is if you I'm just gonna give you the intuition. Here, this is it, and so you input on one of these data points, for example, this purple one. So at the end, you expect that the output of the neuron here is going to be telling you that the class is class 1 or class 0, depending if it is red or red or purple, the input, right? So then you measure the difference. For example, you give a purple one, and then you get that is red, then there is an error because you expect actually that the output is going to be red instead of purple, or vice versa, and then you just have these errors, and that's what is called in general. We can call it an error, or in general, it's going to be called a loss function. Just to measure how good it's just a way to measure how good the neural network is doing, is performing. And the intuition here is very easy because if you give purple and then it tells you that it's red, then it's making a mistake. So you measure that just as a numerical value, and then you compute all the errors, and then you add them up, and that's going to be the loss. That's the intuition about that. Okay. And what is SGD then, Freddie, and the other students?
Stochastic gradient
Descent, right?
descent.
Yeah, stochastic. It's one of the many ways, and that's actually what's behind path propagation. So, and there are variations of that. Of the stochastic variations, there are thousands already by now. That I remember that in the 80s, in 90s, there were many other proposals still they're working on that just to make it more efficient, but it's just basic on calculus, okay? And it's just an optimization problem. Let me just say, let me see, gradient descent, just to give an idea. And Professor Fabio showed it in the video, but he didn't spend much time on that. Maybe a video would be. I just want to show. Let me to work. Oh, it's too long, maybe. The brown. Sorry. Maybe he said. Just to give a big. Oh, here it is. The intuition, just the intuition. Let's see. I don't have the. So just here as an intuition. So you give a number. For example, if this was the case, you give a digit, and then at the end you get the wrong answer. And then what the backpropagation does is just goes back, changing the values, the numerical values here of the synaptic weights, just to get a better answer at the end. You know, and I just wanted to show, and that's what happens in the middle. But I just wanted to see if they have the figure. By the way, this is a very nice, if you want to know a little bit more, for those who may be not familiar with it, or you can take the neural networks class next term. If you wish. Very interesting. Let me just share this. You can watch it later, but that's not the one I wanted. I just wanted to show this is it. This is important. This is the one that I want. So it's actually an optimization process. So what happens in the end, this is a graphical way to show what is happening. See? Is that you start with some particular combination of values. And then at the end, what you get, there is a scalar field here. You start somewhere here. And then at the step by step, you are moving the values. And then you go downhill here until you get to an local optimum. And that's what happens in general. This is based on calculus. And it's actually the idea and the math is very simple. I mean, if you have studied calculus. Okay, I think we can leave it like as that. And then, so this is a way to do it. It has some parameters there. So I don't know if you can anybody give an explanation at least of this one? But it's called, what do you call this LR?
This is the learning rate, the rate of change that it hopes to expect to reduce in each iteration.
right, Freddie? And so when I say that it goes moving downhill step by step, is how fast, or how big are the jumps there as you go downhill? You know, it could be a short step or it can be a longer step. Okay, right, Freddie? I mean the intuition behind it, and this is all the meaning, but we are not going to go into that. And at the end, what comes next? Oh, here's where you guys had there was a problem, right? And maybe this is very important. Who can tell me? Maybe you, Freddie. I can tell that you're familiar with it.
Yeah, this is the fitting of the model. It used the X train and the Y train to train the neural network and apply the optimizer and the loss function to optimize the model and improve the classification of the model.
So this is actually a way, just by a single, by just a single call to a function here, you just get the optimization of the model, of fitting the model, finding the model, right, Freddie? And you just tell the system here, the program, just look, I trained the neural network with this data, right, Freddie? This is going to be the input. This is going to be the output that I want. And can you tell us, or anybody else, can anybody tell us what this means? Epoch 100?
This is the number of batches that the model will train. It split the input and data into some batches.
No, don't say it like that. I don't like it. Maybe there is a better way to explain it.
The number of iterations that it will perform.
Yeah, but manual is there. Is that manual?
Yes.
Yeah, but wait, what is one iteration? Because maybe iteration is not the right way to do it. To say it, but rather epochs. But what is an epoch?
Let me remember.
Yeah, you saw the neural networks class. You forgot it already? Anybody else? I don't like when you say, Freddie, maybe you're being too specific when you say the batch, right?
Okay, it's pass all the inputs and outputs.
There you go. Say it again, please. Explain it.
Pass all the inputs and outputs through the network.
Exactly.
And apply the loss function.
Exactly. Just by passing the whole data set one single time is not going to be enough. So you need to do it, repeat the process over and over. So you pass the whole data set once, then you pass it again another time, and so on. So you passed it in this case 100 times just to adjust the model, because one single pass of the data is not going to be enough, right, Freddie? Right, Manuel? Did you remember that?
Yes, now I remember.
Right, you don't say an iteration, but rather an epoch. An iteration could be maybe just one single data point. Okay? And at the end, I guess you just you have already the model, and then you can do whatever you want with it. For example, you pass the data over the data points, and you see what the results are, right? I guess this is what we're seeing, right? Who can tell me what we're seeing there? This is already the results of the classification, right? Right?
Yes, these are the boundaries that the network sets.
Okay, is it perfect? Is it good? Is it bad? And I guess we can stop here before the break. For the break, I mean. How good is it? Is it perfect?
It's good, but not perfect.
Who said that, Sergio? Right?
Yes.
Because here, for example, you see this. For example, here, let me highlight this. Right, Sergio?
Yes. Yes.
Because for this point, what do you think the answer is going to be for this particular model? Is it going to say that it's red in this particular model?
No.
What is it going to say? Was it Daniel who said no?
Yes. I think it's gonna be say is blue.
Okay, so the answer of the model is gonna say that it's gonna be that is blue, but you can tell that it's red. Okay, and I think we can take a break, and then you can we can continue with the video. Okay, because we need to go over data more graph neural networks. Okay, and you can continue looking at the at this notebook uh, outside the class. So you're encouraged to do that. But so it's 7:43. So 10 minutes, 7:53. Okay, and we'll meet again in 10 minutes. Okay. See you in 10. Okay, guys, are you guys back? Okay, so we'll continue playing Professor's video. And then in this second part, we're gonna show an introduction to graph neural networks, okay, which is like closely related to what is network science in this context. So it's just as an introduction. So neural networks are going to process graphs directly, as opposed to just a single vector, but we are going to see how they do it, okay? So, okay. Let me just maybe fast forward this a little bit.
To train animal parameters, but
Okay.
The class, the true class.
Okay. Oh, by the way, this is, yeah, he's talking about cross entropy, which is one of the measures, you know, like, or the ways to measure how good the neural network is performing. Okay, let me just move forward because we already did this. And okay, here maybe.
you really need to understand better what's going on. Okay. 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 Good. Great. So let's move to the next part before going to
Professor,
the
I don't know if this is, sorry for disturbing you, if this is the right time to have our break, our usual break.
etc. 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 Okay.
Yeah.
However, some people this like a bots with 7. Okay. The link to this document is in the material of the class.
Okay, by the way, I just posted I just shared it. Please go to the link and follow it as Professor Fabio is giving the explanation, okay? So a gentle introduction to graph neural networks.
Okay, so actually, this is an interesting experiment. It was a kind of journal that had like kind of interactive papers. I didn't know about this. And actually, this was like an experiment that lasts like for 5 years or something like that. But it didn't continue. That's bad, but because yeah, I realized that this has a lot of work. However, some people, this document in particular, actually, I will use it as a kind of presentation because it's interactive. Was done by some people from Google Research, and it has a lot of work and is very good. So I really recommend you to take a look. I will go over it with I mean, no in depth, but I will choose and explain some things. But I suggest you to read it because it is very easy and very didactical. Can you say that? And yeah, it is very good. Okay, so what's a graph neural network? So the idea of a graph neural network is basically to have a neural network that is able to exploit the characteristics of graphs, which are very particular, okay? Which are very particular, okay? So, what are we interested in a graph? That's something that you have already studied during the course, but from the point of view of machine learning, really you have information at different levels. Okay, then you have information at the global level. Okay, for instance, so those are some kind of attributes that you may get from a graph: the number of nodes, the longest path, okay, the diameter, etc., etc., etc. And actually, you have studied many of those. Okay. In addition, you may have information on the nodes. Okay. So, which here are called the vertex. Okay. For instance, if this is a network or a citation network where the nodes are papers and the edges are indicates that one paper cites another one. This could be information about, in each node, you may have information about this paper. Actually, some representation of the text on the paper, okay? So those will be the vertex attributes. If this is a social network, this could be information about the profile of each of the user of the social network. Okay, and then you may have also information on the edges. Okay, the edges. Also, you may have attributes. For instance, if this is a social network, you here may codify the information about the interaction between these two subjects, right? So information about how many messages they interchange, the content of those messages, etc., etc., etc. Okay. So actually, here we were talking about embeddings. So actually, for a graph, we may have some kind of representation that for vertex, for vertices, for edges, and also a global representation. Okay, so the challenge of dealing with graphs when we try to apply neural networks is how to use that information that is structured in a very particular way. Okay, and it's not very homogeneous. Some analogy that they do here is, for instance, images. Images also have a structure, right? However, the structure in an image is more homogeneous, right? Because images are arranged as matrices, and all the images independently, if those are natural images or images of from a satellite or images, a medical image, all of them are arranged in the same way, more or less. Okay, so that's an advantage. But a graph is something which is really very heterogeneous, and that's really a challenge. Okay, okay. So yeah, you already know this, where to find graphs. So you may have graphs in different contexts. I was talking about images, which are typically a typical kind of data that is processed by deep neural networks. And then actually you can think of an image as a graph. I don't know if this has been discussed already in the course, but yeah, you can think of an image as the pixels and their relationship. So for a particular pixel, there is a neighborhood relationship with the neighbor pixels, right? So you can look in an image as a graph. And actually, this analogy is interesting because the motivation of some of the graph neural networks is to take ideas from neural networks, for instance, convolutional neural networks, which are adapted to images, and try to generalize those ideas to working graphs. Okay, so but again, one advantage of dealing, for instance, with images is that they are very homogeneous. Okay, you can see that in the how do you pronounce that? Adjacency matrix, right? Okay, adjacency matrix is very homogeneous, okay? And that's an advantage that's exploited by a neural network. If you want to take those ideas from neural network from images and extend it to graphs, there are some challenges that you have to solve, okay? Also, you can think of tests as graphs, okay? Because the sequence of the words in the test are in some way a relationship. So also you can look at that and see that this actually this document is written like a motivation from people from machine learning. So they are trying to introduce the notion of graphs to people that work with machine learning. Okay. Now, this is the kind of graphs that you are already used to. For instance, molecules. Okay. Or this is more complex graphs. This is a social graph. These are the interactions of the actors or the characters in a play. Okay, so yeah, and there is a challenge. See, if you are thinking, okay, I'll try to use ideas from the neural networks, from the kind of data that I work on, to apply to graphs. So something that results very natural is to say, okay, the adjacency matrix is like a natural representation of a graph, is numeric, is a matrix. I can feed that to a neural network and see what happens. Okay, what's the problem? Because actually you can think, see, this in some way similar to an image, right? Where you have the pixels, and then yeah, I can fit directly the adjacency matrix to my neural network. The problem with this, oh, okay, this is the another network that you know very well, the karate network. The problem with this is that what happens is, let me, I will uh, 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 skip, I will go back to show what the problem is. The problem is that the adjacency matrix, when you depends on the order of the nodes or the vertices. Okay, so see, this is exactly the same graph. This is the adjacency matrix for the same graph, but what happens here is that the nodes are sorted in a different way. Okay. Yeah, there is not a natural order. Right? Thank you, Ricardo. Exactly. That's what happens. What's the natural order of a graph? There is no natural order. See that in an image, there is a natural order because of the position of the pixels. Okay, but in a graph in general, there is no natural order. And see what happens.
Maybe I would like to highlight that, right? There is no natural order first if you plot or you get the adjacency matrix, or even when you will plot it, plot the graph, right, Professor? Because we have seen it in the class that the same graph you can plot it and draw it in different manners, right? So it looks different, but it's actually the same graph. Something like that occurs also with the adjacency matrix. So if you change the order of the for example, you can number the nodes, but if you can number them the way you want, and then if you change the way you number the nodes, then you get a different graph.
Okay, let me do an observation here. If you permute the nodes, you get a different adjacency matrix, so they are not invariant, and you can't. And as Dr. Fabio said, you can use it for feeding the neural network, because if you disorder the nodes, there's going to be another representation, and the neural network was not going to know which is the normal representation.
Exactly.
But if you use neighbor information, for example, the neighbors are invariant. Yes, my friends are invariant. There are 3 or 4 friends. So neighbor information could be a more permanent and more invariant information of the graph than the adjacency matrix.
Exactly. So I think that point is very important, because exactly what you just said. You need to extract some information that is invariant. That is, it doesn't matter if you change maybe the order or something; it still remains there as a important information of the graph. Let me just continue. Thank you, Professor.
Happens. This is a graph with only 4 nodes. Okay, only 4 nodes, and all these are adjacency matrices of the same graphs. What changes is like the order of the nodes, and then when I move, see here we have actually 1, 2, 3, 8 by 3, 24 different adjacency matrices to represent the same graph. So that's a problem. So like a naive representation of the graph to feed it to a neural network as an is adjacency matrix is something that really will not work. Okay, so that's a problem. Okay, so that's a challenge, and we will see how it is addressed. Okay, what kind of problems we may have from the point of view on machine learning, the typical problems on machine learning? Okay, so we may have, for instance, a problem where each instance or each sample that we want to process is a graph. For instance, this could be molecules, and then I want to classify the molecules according to one property. Okay, so this is a task at the level of a graph. Okay, so each instance is a graph, And then what I want to do is to predict a label, for instance, for each graph. So each graph is independent of the other graphs, and this is very similar to what we typically do in machine learning problems. Then we have problems at the at the level of the node. Okay, so here our problem is I am given a graph, only one graph, and then my instances are the nodes. Okay, the instances are the nodes. For instance, this could be a social network, and then this could be a classification of the nodes of the social network according to. For instance, I want to predict if some of the members of the social network are more willing to buy some product, a cell phone, or less willing to buy a cell phone if I'm using this for marketing. Okay, so the input, my training data set, and I mean, my data set is a graph. And then I have to do, for instance, predictions at the level of the node. Okay. So this is a node level task. Okay. And then we may have edge level task. Here, the example is I have for instance, objects or actors or elements in a scene, and I want to predict what's the relationship between those actors or those objects in the scene. Okay, so really, what I have to, my model has to be able to predict is something which is at the level of the edges. Okay, so this is called an edge label task. Okay, so just thinking from the point of view of somebody that wants to develop a framework for doing learning with graphs, you start to think, wow, that's difficult. How do you represent the data? How do you deal with in the same framework with the same kind of, with all these possibilities that you may have? And actually, that's something which is interesting about the frameworks. Today, we are going to discuss about one framework which is called Spectral. We are going to use it, and we will see how they deal with that challenge. Okay. Okay. I think this is good time to stop for a break. Professor Luis Fernando, how long is the break? 15 minutes? Or
15
15
minutes.
minutes. Okay, great. So it's 7:35. So we'll meet again at.
Okay, so no break, right? We already took the break, so let me just move forward. Okay, so is it clear? Do you know the different types of analysis that you can perform? Let me just move fast forward this a little bit. And as I mentioned, you should be looking at the paper, right? The interactive paper. Let me just see.
Information.
Okay, I guess we're here. We're almost ready to. Let me see to move on, to continue to go on. Okay, here.
Okay. So everybody back. Great. Okay, so as I was saying, it's not clear how to represent the information for feeding a neural network. The information of a graph to feed a neural network, which is true, is that definitely we have information at the level of nodes, at the level of edges, and typically that's the kind of info, the information that we want to model. But eventually we may have additional information, for instance, information at the level of the graph. And the question is how to deal with that information to feed to the network and how to do learning. Okay, so we will see different alternatives. Okay, so here, this is like the kind of the simplest model that we may have. So what's this? So we have a graph, right? And then we have information at the level of the whole graph, at the level of the vertices or nodes, and at the level of the edges, okay? And then here, what we call F is basically a neural network. It is shown here. But see that we process independently the information of the global information, the information of the vertices, and the information of the edges. Okay, so really, what happens is that we keep the structure of the graph, but eventually what we change is the information that is associated to the whole graph, to each node, and to each edge. Okay, and then we can train a neural network to do that. And this, what we are depicting here is what will be like a kind of ledger. Okay, so think of this as a generalization of what we have in a conventional neural network. For instance, in Keras, we have dense layers. Okay, so a dense layer basically what it does is it maps a vector to a vector. So here, instead of having only one vector, what we have is a whole graph that have information at the global level. So different one vector for the whole graph, a set of vectors for each one of the vertices, and a set of vectors for each one of the edges. And then the layer will map all of those vectors to new vectors that will be associated with the whole graph, the nodes, and the vertices. Okay. Okay. So that's like the simplest model that we can think of, where we don't have interaction between the edges and the vertices, or the vertices and the whole graph. Okay. Okay. For instance, something that if our task is a task at the node level, basically what happens is that, for instance, this will be a model that takes the information of the vertex and process the information of each vertex, of each node, and make a prediction that will be like assigning a class to each one of the nodes. Actually, here we are not exploiting the structure of the graph. And in the third part of today's session, we are going exactly to do that. Our baseline model is going to do exactly this. Okay. So in principle, this is a graph neural network, but it's a neural network that is ignoring the structure of the graph. Okay. Okay. Then one possibility that we have to integrate information is to, for instance, what we are doing here. So here we have information about the in the edges, but we don't have information in the nodes. Okay, so how do we integrate the information from the edges to get information in the nodes? Remember, and actually it was good idea. Thanks, Jonathan, that brought the topic of the embeddings, because actually what we are doing here is assigning vectors to different parts of the graphs. In this particular example that we are looking at here, we are assigning embeddings, vectors, to each one of the edges. So we have information about the edges. And then what we are doing is, for instance, here for each one of these nodes, for instance, let's choose this node that has two edges. So what we do is we integrate the information of the edges, which are associated with this node, to get information for this particular node. Okay, this kind of operation is called pooling. Okay, because it's an aggregation of information. So we can use the information of the edges to build information for the nodes. Okay, so graphically we can depict this in this way. Okay, so remember here was a very simple model which we have information at the level of nodes, and then we use that information at the level of nodes, so the vertices, and we apply the function, for instance, a classifier for classifying the nodes. Here, yes, Ricardo.
I'm sorry. It seems a little bit strange for me because the how we know we are zooming all the vectors, but how we know that we are not zooming things that I mean it has to be in the same scale, because
That's
if not
right.
we
That's
are
right. That's right. That's right.
adding.
Yeah, let me give you an example. Suppose that this is a social network. Okay. Typically, in general, I can have information, and these are each node here is a person in that social network. Okay, and typically I can have information of each actor, of each person in the social network, right? However, because of privacy, I don't want to store information about the people, okay, of the individuals. I only store the information about their interactions, okay? For instance, it could be a vector representing the most frequent words of the messages that two person interchange. Okay, so for instance, the representation of this edge here is a vector with the frequencies of the words that the people use in their messages. Okay, so yeah, to do exactly what you said, how can I integrate that information? The information of this edge in some way has to be compatible with the information of this age and information of this age and this age. They are representing the same. They must have the same dimension. Okay. So when I add them, it makes sense to add them. Okay.
Yes, but for example, we have here 4 arrows, and it's summing 5.
Oh yeah, what's the
vectors.
fifth one?
The fifth one is the node, but that I guess I don't know.
No, you know what? I don't know. I don't know, but actually they put this graph to motivate this one. Yeah, I will not put, I will put only the information of the, yeah, you can have the information of the nodes, right? However, really what I want to illustrate here, and I think is what they want to illustrate, so that I don't know why they have 5 and not 4. Yeah, and yeah, you're right, they had one more that could be on the node, but here for this graph, actually what is happening is that you are not using any information of the nodes, you are only using information of the edges. Okay, I
That
will
makes
say,
sense.
yeah, I will say that this is a mistake, but probably I'm overlooking something. But from my understanding and the motivation, yeah, because they said, yeah, here they say we are gathering information from the edges to the nodes. This goes from the edges to the nodes. So yeah, I think they shouldn't have here 3 but 2, for instance, for Nino, and for this one 2, and for this one 4. Okay. Okay, so this is just to illustrate a particular case where, in fact, I can gather information from the edges to the nodes. Okay, and the other and the opposite thing, I can also gather information from the nodes to the edges. Okay, see that all this is about representation of information. Okay, with the purpose of transforming that information. By the way, what I'm showing here is, yeah, these are like the final layer, and these are node predictions, but in general this could happen in any intermediate layer of the neural network, and sometimes these representations are really learned by the neural network. Okay. Okay, so I can gather information from the edges to the nodes. I can gather information from the nodes to the edges. Okay. And I can gather information from the vertices to the or from the nodes to the whole graph. Okay. If I'm going to do, for instance, global prediction. Okay. And then I can combine this. Okay. So typically in a graph neural network, basically what you have is something like this. You have an input graph, and then you have different layers that transform the information that you have at the level of nodes, edges, and at the level of the graph. Okay? Okay. There is some concept that is used as a way of abstracting what's going on when you are dealing with the information in the graph in a neural network, that is mesas passing. Okay. So what was the idea? The idea is that actually you can, for instance, integrate information from nodes that are connected to other nodes. So here, let's see if, in fact, here now this is right, but here the concept that they are illustrating is different. So, for instance, let's see this node. This node has its own information, but it integrates information from the other nodes, from the neighboring nodes. In this case, for this node here, the neighboring nodes are this and this. Okay, so it integrates its own information plus the information of the neighboring nodes. And same for the others. Okay, so this is called mesas passing, and this is typical. And in fact, the example that we are going to look at later, which is one of the first graph neural network models, is what it does. Okay, so in one layer, this is the layer N, we integrate that information, we apply that transformation, which is basically a neural network, some layers of a neural network. Typically is a linear transformation plus some non-linearity. And then at layer N plus one, yeah, we get that integrated information. So for instance, here, this is the node. It integrates information from the neighboring nodes, and this is the integrated representation. You apply the function, and then you get a transformed representation, and this is the new representation for that node. Okay, and for all the nodes, it's exactly the same. Okay, for all the nodes, it's exactly the same process. Okay, so actually, what this does is a kind of generalization of what, for instance, convolutional neural networks do with images. Okay, but this is more general. Okay, because
Okay, I need to stop there for a bit because I don't know if everybody is familiar with convolutional neural networks and what is the idea of what Professor Fabio was talking about. But let me just give just to show what it is about. Okay, so an intuition, because there is actually a definition of the convolution. It's just an integral, double integral, or triple integral. But I'm just wanting to show this in practice for images, because the concept of convolution is for any type of signal, one-dimensional, two-dimensional, three-dimensional, n-dimensional. But it's more popular when you apply it to by the way, I rather I'll share this link to you guys. So what happens here? Let me just see. How do I? Oh, okay. Let me see if I did reloading. So what a convolution does is what is going on here. This is just a convolution. What the professor was saying, Professor Fabio, is just you just look at one particular pixel, you look at the neighboring pixels, and then you perform some mathematical. It's actually pure arithmetic. Like you just multiply the color of the pixel by one particular value, and then you do the same thing with the neighboring pixels, and then at the end you get just a sum, a weighted sum of that, and that's going to be the value of the pixel that is going to be here in the output. That's what convolution does. Okay, and so the ideas he mentioned was exactly a generalization of that, because you step on a pixel here and you pay attention to this particular square there, the dark square here. So what it does is just compute some operation in one particular pixel by looking at the neighboring pixels. And this is, as he mentioned previously, that this is a very homogeneous graph, because only one pixel has we can pick up the 8 neighbors. So it's a very homogeneous, but for example, one of these pixels is not connected to a pixel far away from there, just to the neighboring ones. And that's it. So, and that's what it does with the convolution, but you just look at the neighboring pixels and compute this, perform this operation. With their own color and the neighboring colors, and you just multiply them by some particular factor here, like negative 0.25 or so, and then at the end you just get a particular value that is, if this is going to be the color that you apply here. And as you mentioned, you can extend this concept by, instead of looking at the here, I mean, the pixels or the nodes are going to be close here in the image, but in any arbitrary graph or any graph, they can be far apart. And that's what he does when he mentioned what he mentioned in the video. You just look at the neighboring nodes, and then you perform some linear function of multiplication or something like that, and then at the end you just assign some new value to the particular node, and that's what you get there. I just wanted to maybe stress that a little bit. And let me see where. Yes, I'll go back to this video. Bueno, I'll share the video afterwards, so you can maybe know a little bit more about what convolution is.
Every image can be seen as a graph, but not every graph can be seen as an image. Okay? Okay. So this operation that we are doing here can be seen like this. It's like you use the information of the nodes and the neighboring nodes. So this is like a transform from nodes to nodes, and then you apply some function, and then you get the same graph but with new information. Okay? And then you can do different combination of all these. Then, for instance, here you can send information from integrate information from the vertices to the edges, and from the edges to the back to the vertices. And then you can interchange that, for instance, from vertices. This goes from edges to vertices, vertices to edges, and then in parallel you do the same from the opposite, from edges to vertices, and from vertices to edges, and to edges to vertices, and then you can combine all that. So see that the possibilities are multiple. So different graph neural networks use different combination of these strategies. So this is a kind of general framework, okay? And then you can add the global representation and things like that. So the important thing here in a graph neural network is how it integrates all this information. Okay? Okay. This is an example of a model. This is a task at the level of the graph. Okay, so this is something like this, like the first one example that we saw here. So each instance is a graph, okay, and then we want to classify, for instance, in two classes. So this is a real problem where we had molecules, and we want to classify those molecules according to some chemical property, okay? The chemical property is this one. Yeah, you want to classify according to the odor. Actually, there is an odor data set, and it has some labels that are associated with the per sets. And in particular, in this example, they want to classify the smell of the molecule as pungent or non-pungent. Pungent is a strong, striking smell. For example, the smell of garlic and mustard, okay? Okay, and that's what they want to do, classify between pungent and non-pungent. Okay, so here, every point here, if you click upon here, you will see the molecule at the right. Okay, so this is the molecule at the right, and then this is the output of the model. So the inside, the color inside each circle here is the real label of the, sorry, no, is the prediction of the model. And the circle around, the color of the circle around is the classification, okay? So for instance, this one is a sample that is well classified by the model because it's pungent, and the model prediction is pungent. And this is an example of a bad classified sample. Okay, the sample is pungent, but the classification of the model is only 2% pungent, is non-pungent. Okay, so what you can play with here is with different configuration of the network with different aggregation functions to aggregate. This aggregation function is how you, for instance, aggregate the information of edges to vector, from vectors to vector, or from sorry, edges to nodes, nodes to edges, or nodes to nodes. Okay, and then you see if you have information at the level of node, at the level of edge, or at the level of at the global level, and then the size of the embedding, how large is the representation for each one, and this is showing you the different models. Okay, AUC is the area under the rod curve, which is a measure of how good the model is doing it. You can see that different combination produce a different performance of the model. The bigger the better. The optimal value will be 1. Okay, and here they have a graph comparing different configurations. And then here is the test AUC. Okay. And this is the number of parameters of your model. So see that not necessarily to having more parameters is better. Okay. So actually this one is a good, is the best performing model. And you can see the different parameters, and it's not the one that has more parameters. The number of parameters, this is 10,000, and the number of parameters here is like 100,000, around 100,000. Okay, so yeah, this is interesting. You can play with this and interact with the visualization. And yeah, there are different analyses here. Okay, so as I was saying, this is very didactic document, and I encourage you to take a look and to read it fully, because I overlooked many things. It was just a very general skin over the document. Okay, so and there are several problems, and definitely the area of research on graph neural networks is very large, and is very active, and they are doing very interesting things. Okay, okay. So for the end part of our session today, we will work on this notebook.
Okay, this notebook. Did I share this? Did I share the link? Can you guys confirm? Did I already share it with you guys? It's not. I guess not, right? Did I?
No.
Sorry. It's posted there on Classroom though, but I'm gonna share it right now. I thought I posted it here. Can you please let me know if you can access it? By the way, I just shared also the link to convolution network explainer. Okay, just in case. Okay, so you can also view it. Can you tell me if you can view, have access to this collab, to this Python notebook? Okay, so I'll then continue. Okay, and you please follow the notebook as Professor Fabio is giving the explanation.
You have access to this notebook, and I will work on it as we go today. So I ask you to please open the notebook and follow along what we are doing. Okay, so that you get a better idea of what we are doing and try to run things. And I think it's more interesting. It's exercise is going to be more dynamic. Okay, so this is not complete yet. I will add things. So every time I add something, I will save it. So if you update your notebook, you will get the updated version. Okay. Okay. So the link to this note, I will post immediately the link here so that you can follow along. Okay. Good. Great. Okay. So what's this notebook about? So this notebook is basically we are going to work with a data set. And the task that we are going to work on is a node classification task using graph neural networks. Okay, so we are going to use Keras, two frameworks. We are going to use Keras, and then we are going to use also Spectral, which is an specialized library that works with TensorFlow for doing graph or learning, deep learning over graphs. Okay. Okay. Good. So here this is initializing. So there is a data set which is a very popular data set. It's a citation data set. I don't know if you already work with this in the course. Is a data set made of a scientific publication, 2,708 scientific publication papers, and they are distributed in 7 different classes. Actually, there is a description here. So these are the 7 classes: case-based, genetic algorithms, neural networks, probabilistic methods, reinforcement learning, rule learning, and theory. These are papers about machine learning, okay? And then we have information about the citations between those papers. There are actually 5,429 links between those papers. And each paper is represented as well by the some vocabulary, the presence of some words, and the vocabulary, the size of the vocabulary is 1,433. Okay. Okay, so here are the references to the relevant papers of this data set. Here we are going to download that data set. It's small, you can download it very quickly. You will see that you will get 2 files, one with the representation of each one of the papers and one with the information of the links of the graph. So those are the sites. And then, okay, and a readme that this one that we have here. So what we are going to do is we are going to use Pandas, which is a framework for dealing with data in Python to load the data set. So here I am loading the citations. And then you can see that is actually here we can visualize it. This is a sample from that data set. So here is like the idea of the paper, and then we have the target and the source. So that means that the paper sorry, this is just a consecutive number. No, the ID of the paper is this one. So this means that the paper with ID 33303 cited the paper 15600. Okay. So here we have 5,000 of those links. And then we load the information of each one of the papers. So we have 2,700 papers, and each paper has these 1435 attributes, and the attributes are the paper ID, which is here, then 1433 binary values that indicates if a word is present or not, and then the subject of the paper. So here, yeah, we are showing the content. The different fields are here in the vertical. So we have the paper ID, then we have the term 0, the term 1, etc., till the term 1432, and then we have the subject. Okay. Here we do some pre-processing. Okay, so these are the counts of the paper for each one of the classes, and then here we do some pre-processing to for instance, instead of using the name of the class, we are going to put a number, and instead of doing we are going to have like a consecutive ID for the paper, etc. So that's what we are doing here. Okay, so let's visualize a portion of the graph. Okay, so this is here. So let me copy this. So with this code, we will visualize a portion of the graph. We are only going to visualize 1,500 connections or edges among the papers, okay? So yeah, this takes a little bit. Okay, so now we have the visualization, okay? So you can see here, this is just a portion of our graph, okay? Visualize, okay, just to get an idea. The colors are associated with the labels of the paper. So what you will expect is that papers which are related have more connections between them, okay? But first, what we are going to do is we are going to build a model. So we are going to build a model, a baseline model that is going to ignore the structure of the graph. We are only going to use the information in each one of the papers, okay? So it's a very simple model. These are like let's take a look to so here we have some functions to run the experiment, to display the learning curve, okay? And then this is our model. So yeah, this is our baseline model. Let me. Okay. So yeah, so this is a helper function to create a block. This is going to create a number of blocks that have this structure. So you have a dense layer with some pre-processing layers that are that do some kind of regularization. Regularization means operation that makes that control the complexity of your model. Okay. And this is the function that builds our baseline model, and probably it's easier to look at the model here. So basically, you have here, this is a conventional neural network model. This is not a neural network model. It's just a conventional neural network model that use only the information of the papers. It doesn't use the structure of the graph. Okay, so it has 3 blocks. You can see. So here.
Is that clear? Can anybody tell me why does he say that? That it's actually not using the structure of the graph? Is that clear, you guys? Why is that? Hello, are you there? Are you still there, or did I lose you? Are you lost? Let me see who. Freddy. Why? Why is this, Freddy?
I think that they are gonna use the reference or the some kind of features of the original data, not the relations between the different papers, maybe.
Yeah, but what? Yes, yes, but what information in particular are they using here in this example, in this first model, rather? What information did he say that they are using in the model?
No, I don't know.
He said it. Anybody? Remember, we still have a graph, right? Because we have the Freddy. We have the papers and the citations, right?
Right, right.
That's how we have the graph. But in this example, this particular model, rather, uh, what information are they using as input to the model?
Only the information from the notes.
Who said that? Was it you yourself?
Santiago.
Oh, Santiago, where is it? Yeah, because I heard a different voice. Yes, Santiago. Just the information about the books, right?
Mm-hmm.
Santiago, their papers,
Yes.
and then so the notes, just information about the notes. So you don't know anything else. You don't know anything about the structure of the graph, right? You don't use it, rather, right, Santiago?
Yes.
So you miss it. So it's just a traditional, let's say, model. So you use a graph as an input, but rather just the information about the nodes. Okay, the simplest model. Okay, let me just continue playing.
Sorry, it has yeah, several blocks. So it has 1, 2, 3, 4, 5 blocks that are like this here. Okay, and then you can see it received 1433 because remember the number of features or the number of terms that represent each document is 1433, and every layer has 32 nodes, so you can see the different layers, and at the end you have a dense layer that is the output of the model that has 7 neurons. Why 7 neurons? Because we have 7 classes. And in total, our model has a total number of 62,500 parameters. Okay? Okay. So that's our model. This is a graphical depiction of our model. It has something which is usual in neural networks nowadays. Is something called skip connections. So you see that the layers, our model is not sequential. It's have some connection that skips some layers. Okay, and those skip layers basically what they do is they improve, they make the network more easily trainable. Okay, that's what they do basically. Okay, so that's the model. So this is a conventional neural network model, a state-of-the-art neural network model. So it's not a simple model. Okay, then we are going to train it. Train data is not defined. Okay, let me see. Probably I didn't execute something. Yeah, this one. Okay. Okay. Good. And then we are going to run our experiment. Okay. Okay, so yes, please. I don't
Uh,
see who is raising the. Yeah, yeah. Please go ahead.
just to make sure that I'm understanding well,
Sure, Ricardo. Of course,
the,
that's the
the
idea.
the idea is to make a model to predict the topics,
The class, yeah.
the
So
class.
we have 7 classes. So these are papers from seven different
Okay.
classes. Some about
Based
neural networks, some about probabilistic methods, genetic algorithms, etc. Okay, so what we want to predict is what's the topic, yeah, as you said, of the paper, right?
based on the words.
Only on the words that are present in the
Okay,
document.
that's
Okay.
our model, zero model,
Our baseline model. Yeah,
baseline model,
that's right.
and to
Exactly.
improve it by adding the information of the net of the citation. That's the idea.
That's the idea. So we are going to use a graph neural network that use the citation graph to do the prediction, and we will see if it improves. That's what we expect.
Okay,
Okay.
thank you.
So yeah, that's the idea. So let's see how it performs. So yeah, it's going fast. So we have a train validation. You can see that it is it's already done. Okay, yeah, because here probably we are using patience. Let me see. Yeah. Oh, okay. Yeah. Here, yeah. Actually, let's plot the graphs of the training to see what we get. It's easier to look at the learning curves to see how the training process went. Okay. So yeah, let's. So these are our learning curves. So what was going on here? So these are the different iterations, epochs. An epoch is a full pass over the whole training data set. And then we are plotting both the training loss and the test loss. And we are also plotting the accuracy on the train and test data set. So you see that the accuracy improves like around almost 90%, but in the train data set, but in the test data set, it reaches on maximum probably here around, let me see, how much was that? Yeah, probably around 70 something. Okay, yeah, probably almost 80. No. It didn't reach 80. Okay, and it goes down. Okay, so yeah, probably here it's doing overfitting. So this is like the best it got. And we can evaluate because this is actually training and validation, not tests. And here we can evaluate on the test data set, and we get an accuracy of 73%. Okay,
Teachers,
73%
how do you
using a
define
yes.
the training data? The number of training?
Oh, yeah, here, basically, yeah, let me go back to the, yeah, I didn't talk much about that, but really what we did here was to partition the data set more or less in half for training, half for test. Remember that this is only one graph. Then our instances here are the nodes of that graph, the papers. Okay, so we use half of the nodes for doing the training, and we keep half of those nodes for doing testing. Okay.
Okay, the question is more related. How do you define correctly from half to training, half to
No, that's arbitrary. That's actually
okay.
no, that's arbitrary. Uh, yeah, actually, if we go to the original to the papers that use this, typically they use less for testing. Okay, it depends. It depends. For instance, in the original paper of the model that we are going to use here, yeah, actually, we can go to the paper. We can look at that. Yeah, actually, I have a link to the paper. Yeah, probably paper is here. This is one of the classical papers. It's called Semi-Supervised Classification with Graph Convolutional Networks. So in this paper, yeah, I come back to this. But in this paper, they use this same data set, is the Cora data set. This is the one that we are using. Okay. And label rate means, since the purpose here was to show that just with some small number of labels, you may have a good prediction for the full graph, they use only for training the 5%, not 50%, but the 5%. Okay, in this paper, and actually they get pretty good results. For Cora, they get around 81%. Okay, so yeah, it depends on what you want to do. No, in this particular paper, the purpose was to show that just with some small number of labels in your notes, you can predict the rest. Okay.
Okay, thank you, teacher.
Yeah, but it depends on what was the purpose of your experiment. Okay, good. So, yeah, so the learning, okay, so the accuracy here is 73%. So now we are going to use another, yeah, let me copy this because I need to start some things. Okay, we are going to use a software which is called Spectral. Okay, it's a framework. Give me a moment. We'll go right away to Spectral.
Let's see. I think we need to stop here. I just shared the video. I think we have the first example. So please let me know if you have access. This is the video to that session to professors. So we're missing just the last part of it, but I think you can just go over the spectral part on your own. And then I think I'll post some material for the next session, so you can view it before we have Professor Farias talk. Please. So I hope you understood what he said. I think it was very, very well explained. And also just go over the paper. Remember the paper that he's followed, the interactive paper, so you can reinforce the concepts, so you can get better understanding of the concepts. Okay. So, Professor, next time is gonna be Wednesday, May the 1st. Is it that true?
Yes.
It's gonna be a holiday, right?
Holiday.
So we are going to see you guys in 2 weeks. Meanwhile, of course, you're busy, right? What are you doing? You're working on your final report of your project, right? So that's gonna be a few weeks from now. Okay, that's gonna be like the closing of the class. Okay, so keep working, and we, as usual, we are just there for you guys. Freddie, why are you sad? Freddie, I saw your reaction. You're crying.
Because it's a lot of work.
Oh, but you're strong. You're brave. So you can do it. You guys can do it. Okay. Okay. So thank you so much, guys. Have a good evening and get some rest. And we continue studying this graph neural networks.
Thanks. Have a nice evening, everyone. Bye.
Good evening to you all.